Welcome to this session, Bridge the Construction Manufacturing Gap with Inventor Product Templates. In this session, we're going to cover changing the construction industry by moving away from project-based mindset to products with product templates created in Inventor. I'm Andy Akenson. I'm a software architect here at Autodesk. Over the last 14 years here at Autodesk, I've worked on the Inventor product, getting Inventor technology into the cloud in our Forge platform, helping our customers automate their workflows, and for the last year and a half, I've been working in our industrialized construction team. I've been working on helping our customers bridge the gap between construction and manufacturing and helping automate the process from end to end.
I'm Justin Rice. I'm a solution architect in the consulting organization of Autodesk, and I work with some of our largest key clients to define and implement workflows based on our latest technology. In order to ensure the workflows align with the roadmap of our technology, we need to work closely with the product development teams. Specifically, I work very closely with the team Andy is on to understand the workflows in industrialized construction that are being developed. Prior to joining Autodesk, I spent 20 years in the field working with clients to develop design automation applications. Those applications were focused on capturing the rules and the logic behind product templates, reducing the amount of effort it took to generate those designs, improving the quality and the standardization of those designs, and finally eliminating redundant tasks. Some of my solutions have reduced effort from weeks down to hours.
So why do we need to build this bridge, and what is this bridge trying to span? It all starts with our vision. We want to help accelerate the adoption of industrialized construction by connecting design and make tools and enabling a data-driven process. So if we look at what some of our fundamental customer challenges are, if we start with the architect, they're often working with early design decisions that have to be made without knowledge of manufacturing feasibility, costs, or sustainability. The construction manager is dealing with manufacturing detail that is defined after the design decisions have been made. And the subcontractor, the data they're working with is often incomplete, missing detail, and often has to be manually recreated. Now let's hear directly from three people in the industry that are having to deal with these challenges today.
We originally, did the thing automated prefabrication and had that chunk, but it's not connecting with the other stuff.
Yes.
And we do our own engineering, so we should have an advantage.
Right.
But we're finding all these bottlenecks and one big value stream is the idea, but it's hard to implement without the tools and the data and pulling it all together.
Right.
What we're doing now, we're beginning to treat, for years we've heard, just design it and we'll figure out how to prefab it. Do whatever you want and we'll figure it out. That doesn't work.
Right.
Because the rules, the data, the information comes in after the design is done, and then it throws us into this monster.
And that's not
cycle.
working.
It's a nightmare.
And like we, one of the things that struck me working in the design field was that there was, especially in like a hard bid process, there's no feedback loop at all.
Right.
I'm literally sitting in an office detailing something, without any ability to check with the actual people who make that thing in a meaningful way and collaborate with them around that information. So it's about bringing the making into the design.
I love that.
Versus sort of creating a design and hoping it can be made.
Exactly.
We have to kind of flip the script, I think.
I love it.
So you were asking me a question 5 years ago, what did I design in? I designed in fabrication in AutoCAD. 2 years ago, if you would have asked me, it would have been, what are you designing in? And I would have told you, we're in Revit now, we're doing Revit, wow, this is great. And I come here today and we're designing an Inventor. And that just tells the whole story, right? Because Inventor's manufacturing, and you can't manufacture without an Inventor-like product.
So to summarize some of the needed capabilities, the architect needs to be able to design with assemblies that are informed by what can truly be made and modified. The construction manager wants to clearly define and share what assemblies can be made and how they can be modified. And the subcontractor wants to be able to extract assemblies from the project to automatically create things like models, drawings, bills of materials, quotes, and not have the amount of rework that happens in today's project-based environment. So if we look at the current flow of the project today, it starts with the owner informing the engineer of what products can be used, who then hand that off to the architect to consume that in their design. They then send that to the fabricator, who then sends that to the site to be installed. Now, any problems that are found in the field come all the way back to every step along the way, causing scheduled delays, extra cost, and waste in the entire cycle. Productization comes in when we start informing the design for the architect from what can actually be made, so the fabricator can expose what the inputs are, so the architect's always working with fabricatable elements to help reduce issues in the field. This is where productization for construction comes in. Using a dynamic product template in Inventor, it provides that bridge between the design and make so that we can inform design with customizations, we can automate fabrication information, we can define exactly what is made, how it is made, and define what the allowable variations are. So we can provide things like levels of detail or full detail for manufacturing, shop floor drawings. This is all about providing the right information for the right people. So that a non-CAD user can access the models and generate content, we can derive a wide variety of information from one single source template. And we end up with a one-to-many relationship where we can generate many unique linked instances from a source template. So if we look on the left, we've got a dynamic product template in Inventor. We can bring that into something like the large model viewer in Forge. And from that, we can generate many different kinds of outputs.
Okay, now let's take a look at productization in action. Within the consulting organization, we'll be working directly with Binsky and Snyder, who is an 80-year-old mechanical contracting firm who is recognized as one of the most recognized mechanical contractors in New Jersey and Eastern Pennsylvania. Binsky delivers high-quality workmanship on projects from large traditional construction to commercial HVAC, plumbing, and emergency service. And they combine state-of-the-art technology with experienced engineers to bring unparalleled client satisfaction, budget management, and schedule delivery to projects of all sizes. The focus of the project with Binsky will be to take their already developed bathroom battery and extend the capabilities of this product. The bathroom battery is a common building assembly, but it's complex to fabricate on site. The number of variants depend on the number of stalls and the type of fixtures to be put into the bathroom. Are those fixtures either urinals or water closets? By productizing this bathroom battery, Binsky has been able to realize a 40% reduction in costs and the ability to assemble this product 66% faster when it was been prefabricated. Moving this into more of a product and less of an on-site fabrication has enabled Binsky to transition from a traditional subcontractor into a manufacturer and really start to become part of the design team while embedding their knowledge of the fabrication processes into the design process and ensure that fabrication knowledge informs the design of that new bathroom.
In this section, I'll cover what a template is, why they are important, and I'll walk through some samples of how they're actually used today. So if we look at templates in Inventor, they start with a highly engineered, configurable dynamic model. Parameter values are changed, rules are run, outputs are then generated for things like shop floor drawings, bills of materials for the supply chain, or downstream consumption for things like BIM or visualization. If we look beyond parametric modeling with rules, Inventor supports iLogic, where iLogic enables rule-driven design that provides a simple way to capture and reuse your work. It allows the user to standardize and automate the design process. It's really built around automation, efficiency, consistency, and accuracy. Let's see what this looks like in Inventor with a simple wall assembly. In Inventor, I have a parametric wall assembly. It contains things like top plates, king studs, bottom plates, cripples for above the door, and patterns for laying out the wall. It also has an associated drawing to show things like stud placement, overall width and height, and door position. The assembly is constructed with model parameters as well as user parameters for things like the stud spacing, or the stock, or the overall wall width and height. We can also get a hold of the bill of materials so that we can manage the materials for this wall. In Inventor, we have the capability of adding iLogic rules and a form. Here I'll show changing the stock size, make the width 12 inches. Let's change the wall width, the wall height, and we'll modify the door. You notice as we make these changes, we don't just stretch the wall, but we also reposition the studs based on the rules. The drawing also gets the parts list updated, and when I update the sheet, you can also see the layout gets updated for the dimensions. Now if we go back to the bill of materials, you'll see it's been updated based on our wall changes. Let's take a look at the iLogic rule. We have a configure rule. Anytime a parameter changes, this rule is run. So we have things like the stud spacing, the stock, the door distance, how far the door can actually be positioned, and how the studs and cripples and jack studs are actually laid out. These are all tied to Inventor parameters. Anytime those parameters change, these rules run. See, we also have rules in the drawing, so that when the drawing updates, we can get the intents from the drawing elements, and we can relay out the dimensions. So here you'll see us getting the dimensions for all of the various aspects of the wall, and then relaying those out based on the pattern. All of this code will be available in the handout for you after the class. Now let's look at a more complex assembly. I have a balcony that's made up of parts and sub-assemblies for things like the decking, the handrails, and the glass panels. Here we'll see the parameters, a number of user parameters that drive the model parameters, but the main are the width and the depth. And a more complex bill of materials. So this is for the entire part and sub-assemblies for the balcony. We have an iLogic form, and as we change the width and depth of the balcony, you'll be able to see things like the glass panels change, as well as the decking configuration. Things like this would be hard to do in parametric modeling, but with rules, it's pretty straightforward. So here you'll see my rule, so that every time my parameters change, I can do things like changing the deck count, I can do my glass panel layout, I can reset the handrail, and I can set some extents to make sure that the balcony never goes over 5,000 millimeters. And here you'll see the bill of materials update as I made those changes to make my balcony bigger. Now I can also do things like setting a model state for a BIM so that I can simplify it for consumption in Revit. Here you'll see I've done some replacement as well as suppression. And I also have some rules around setting the level of detail for export into BIM. Now that I've shown you what can be done in Desktop Inventor today, let's take a look at what can be done beyond the desktop in Forge, Autodesk cloud-based offering. Going to forge.autodesk.com brings you to our cloud-based developer platform This platform has all sorts of materials to help you glue together our desktop and cloud-based offerings into single coherent workflows. If we look down, we have specific services around things like viewing, access to the construction cloud, and design automation API. We also have a sample configurator. So I've uploaded my configurable wall product template from Inventor. You can see here I've surfaced the user parameters, so I can do things like changing the stock size, changing the stud spacing, and changing the wall itself, all within a web page. This is the Forge embedded large model viewer. And then once I've made these parameter changes, I can update the model. It goes through the design automation API and returns an updated model. I can then extract the bill of materials for that updated model, as well as get drawings. So here this reflects my changes. I can export a PDF. And I can download things. I can even download a Revit family and open up that configured Revit family in Revit. This allows us to connect the Inventor template directly into Revit through Forge. Resources, including sample code to build a solution like I just showed, are available on forge.autodesk.com. Leveraging Forge, Inventor, and Revit, I want to show you what can be done tomorrow to seamlessly connect the industrialized construction workflows, starting with these highly engineered product templates in Inventor. Using the large model viewer in Forge and design automation, I'm able to extract all of the assembly and walls in this Revit model in a web browser. I'm then able to map the Revit elements to the Inventor product template parameters and generate outputs for every selected Revit element in the building. I can then go to Construction Cloud and see things like the bill of materials for each Revit element, updated models for downstream consumption, again for every Revit element. I'll be able to see the specific Inventor variant that was generated for those parameters. I can see it both here in the Forge viewer, as well as take that Inventor assembly downstream for manufacturing. I can also generate all of the production drawings for every element in that Revit model. And here for this Revit element, you'll see we've generated 2 sheets of drawings. You can see we were able to automate at scale 319 Revit elements in under half an hour in a process that would have been both error-prone as well as set the project back by days, if not weeks or months. The key to bridging the gap between construction and manufacturing using Inventor product templates will be shown in this example, how we can provide a product template that is directly consumable in Revit. This will lead to the Revit designer being able to access all of the input parameters as well as being able to execute the rules so that everything that the Revit designer consumes is fabricatable. Going back to our balcony assembly in Inventor, I now can publish this to the Construction Cloud. I can publish my levels of detail. And then I can also create a marketplace or product catalog based on those templates that are published. I can change the parameters. I can add them to my cart. Now that I have my cart, I can go to Revit and place those balconies in my building. I'll insert the 2 balconies that I have based on the BIM level of detail in my product template, and I'll insert those directly in Revit. And be able to see that in my model. And you can see it brought over the right level of detail as well as the right configuration for each of these rooms. Now I have some other rooms that are smaller and I don't yet have them in my cart. I can go directly in Revit and make the balcony smaller. I'll again select the BIM level of detail and insert that directly in the building. And you can see here, not only did I get the right size, but I got the right panel layout. So I've now inserted something that is directly fabricatable, and I can even go and submit a bid directly for these components. Now we can deliver a completely connected workflow. So if we look at the gaps between the engineer designing the product template and the installer on site, we have the owner who influences which products can be used in the project. We have the engineer designing the fully configurable, highly engineered product template. They publish that template to Forge. They can then inform the design, whether that's in something like a product catalog for a non-CAD user or a designer directly in Revit. They can then pass that on to Make for people like the sales engineer, the production manager, the fabricators working in tools like Forge Large Model Viewer with their back-end tools like SAP. They can do configuration directly in a website, or they can take it to Fusion for fabrication. And then they can take that directly to the installer in the construction cloud. So now there's a direct path back if the installer finds issues that can inform Make, it can inform the design, it can inform the product template, or it can even inform the owner to know which products to go with in future projects. And hopefully this shows the power of bridging that gap between construction and manufacturing by moving the fabrication and manufacturing inputs into the design process so that not just the Revit designer, but everyone along the entire chain has access to both a single source of truth and any of the derivatives that come from that.
All right, now let's take a look at this connected workflow in action on the Binsky modular carrier. So here I have an iLogic model of the Binsky modular carrier. I'm going to go ahead and bring up this form, and I can start changing the configuration of this model. So I can switch to having no water closet here in the fixture 4. I can switch the water closet in the fixture 2 position. You can see right now this is a back-to-back configuration because I've got a water closet in fixture 2 and in fixture 5 to a urinal. And so that'll swap out those two components. Once I have completed my highly engineered design, I can then zip up that model, take the zip file, upload it to the configurator, select the correct top level assembly, which will be my modular carrier assembly, and upload. That will create a new project in the configurator, allowing me to drive those same parameters in the current configurator that I was driving in the iLogic model in Inventor. All right, so you can now see that that model has been uploaded. You can see the cloud credits that were consumed. And now I can go in and start driving those same parameters. So I can quickly switch out and say I don't want a fixture in location 1 or 4, and I also want to remove the fixture in position 3, and then I'll switch the waste direction to coming out the right side. Click Update. Those parameters are then pushed into the model, and the iLogic rules are ran based on that set of inputs. All right, so you can now see my new configuration. In this configuration, I can then go look at the bill of material. Here I can see all the components that have been included in the assembly. This specific project did not have any drawings, but I can also then go and look at the downloads. So you can see I could download a zip of the entire assembly. You could also download an RFA. Now this is going to kick off another process. exporting a file from Inventor, pushing that file into Revit, and making a RFI directly from the Revit worker. And finally, I'm going to take a look at this modular carrier inserted into a Revit project. So here you can see a Revit project of this chopped modular carrier has been uploaded into BIM 360. So I'm going to go ahead and look at this full assembly in the large model viewer. And I'm going to go to a front view. And if I zoom in, I can see instances of that modular carrier have been inserted in this assembly where they belong within the bathroom with respect to the entire larger MEP design.
Now a quick recap to show how we're bridging the gap between construction and manufacturing. Let's bring it back to our vision, where we really do want to help accelerate the adoption of industrialized construction by connecting design and make tools and enabling a data-driven process. What we've shown that by starting with a highly engineered product template Inventor, connecting that to Forge, exposing the manufacturing parameters, you can insert that directly in Revit. Connecting the workflows all the way from owner to installer on site and providing feedback all the way through the process. Closing the gap between construction and manufacturing. Now looking forward to answering any questions you may have on the topics we covered here today. Thank you so much for your time, and hope you have a great Autodesk University.